Good morning, everyone. I am S. Vijayalakshmi, working as an assistant professor at SNS College of Technology. Now we are going to discuss about generation of code from tag in code generation. In the previous class, we talked about the intermediate code representation. Now we will see how that is transformed into efficient target code. So we will discuss how compiler generate optimized code using a tag, a directed acyclic graph. Remember that code generation is the final phase of the compiler. So the goal is to convert the intermediate code into a machine instructions that are correct, optimized, resource efficient. So we can also avoid the redundant calculations, maintain the correct evaluation order, and also the minimization of register and memory usage. So objective of this session is we should be able to explain how tag aids in code generation, and also the identify the correct order of evaluation, and also apply tag based optimization techniques. So let us take a real world example. A game developer writing a physics engine. Their code often repeats expressions like a plus b, a plus b, or a and b, a and b. So that is a good compiler should detect and reuse the computations automatically, not reallocate them every time. This exactly what tag based code generation does. So traditionally we could generate code directly from first one is a syntax tree, but it doesn't merge repeated sub expressions. Then however merges identical subtrees. Tag only removes the redundancy and guides them to generate optimized code efficiently. So syntax tree as well as tag tree. So then we got the solution as we systematically generate optimized code that respects dependencies, that is tag approaches. So steps involved in generating code from tag is here the core steps. First one is tag construction, and then order of evaluation, that means perform post order traversal, and then decide the which order of evaluation, then allocate the registers, and then select the target instructions. Then last one is the code generation, generate the final code. So explain that these steps that corresponding one by one. First one is the tag constructions. In this step, we identify common sub expressions and represented them using a single node. This reduces the redundant computations and even helps to remove the dead code also. Since the tag is filled, the post order traversal gives us the correct evaluation order. Then going to order of evaluation and register allocation. First one is the we determine the sequence that represents the dependencies, that is the order of evaluation. The compiler must ensure that each operand is ready before it's used. So and then we going to the register allocation, mapping immediate results to limited CPU registers using methods like graph coloring. Then this keeps the code efficient and avoids the necessary memory access. Then next, going to another topic, instruction selection. Once registers are assigned, we perform the instruction selection, matching the tag patterns to target instruction set. Example, T1 equals C into T, A equal to B plus T1. The compiler identifies optimized like mul, add, etc. In the generating efficient assembly code. Finally, we emit the optimized machine code sequence, and then it ready for the execution like that. Then going for group activity, and build a team A and team B and C. We select three teams. Team A build tag, and then team B label the nodes and find the dependencies, and another team generate the optimized code. Then we look at this sample expression on your slide, this one, and then exactly which computations were reused and which operations could be parallelized, discussed for a minute. This is how tag-based generation makes the compiler smarter and the final program faster. So let us summarize. The tag helps the compiler. First one is detect the common sub-expressions. Next one is the expert dependencies, optimized register usage, and generate a compact efficient code. Thank you.